Now I know what you're thinking. You're thinking making these videos is fun and it's easy. Well, it is fun. But if you think it's easy, I've got something for you. The real math challenge from Mathcounts. Now here's how it works. You make your own video, and you'll see how easy it is. Then you upload your video to realmath.org. And if yours is one of the best videos, then you win a trip to nationals. How awesome is that? So check it out. But not right now, because right now, we've got some math to do. Now, here's our first problem. We're going to form a bunch of products by multiplying 3 different numbers from this set right here. I can do that. So we got 1 times 2 times 3, that's 6. 1 times 2 times 4, that's 8. 1 times 2, I don't want to do this. It's going to take forever, and I might miss some, and we should have read the whole problem. I'll finish reading the problem before we dive in. Among those products, how many pairs of relatively prime numbers are there? Now, relatively prime, that means that the two numbers have no common factors besides 1. So, for example, 2 and 3 are relatively prime. But 6 and 8 have a common factor of 2, so they're not relatively prime. Now, how can we answer this question without listing all these products? I really don't want to do that because I'm a little lazy, so I want to find a smarter way to do this. Well, you know what I'm going to try to do? I'm going to try to construct a pair of these products that are relatively prime. I'm just going to try to make one. I'm going to think about how to make one, and maybe that'll tell me how to count them all. So we make these products by multiplying 3 numbers. So there's my first product, here's my second, and I want to construct these so that the products I get are relatively prime. Now we just saw I can't have 2 even numbers. We're not allowed to have 2 even numbers because they'll have a common factor of 2, won't be relatively prime. So at least one of these has to be odd. Now the only way I can make an odd number by multiplying 3 of these is if I choose 1, 3, and 5. That's the only way I can make an odd number. So that's got to be one of my numbers. Now this other product has to come out to be relatively prime to this one. So when I'm making this product, I can't use the 3 because then I'll have a factor of 3 in common, won't be relatively prime. So no 3. And in the same way, no 5. So once I knock out the 3 and the 5, I'm allowed to have a 1 because we can have a common factor of 1. I'm left with the 1, the 2, the 4. And there's exactly one way to make this other product. We don't care about the order of these numbers. We just care about which 3 we're multiplying to get our products, 15 and 8. They're relatively prime. And thinking about how to construct a pair also told us that there's only one pair. Now I call this strategy constructive counting. Sometimes thinking about how to make one example of what you're trying to count will tell you how to count all of them. Now it's particularly convenient when there's only one to count. But let's try this on a more difficult problem. What we're going to do here is we're going to start with the set of numbers from 1 to 36. And we're going to look for the number of pairs of these whose product is a perfect square. So we'll start off by thinking about how can we possibly get a perfect square product. Now if we start with 1 as one of the numbers, well, then the other number has to be a perfect square. 1 times 4, 1 times 9, 1 times 16, and, well, I mean, that's, anytime you pick a perfect square is one of the numbers. Like if you picked 4, you have to pick the other number has to be a perfect square too in order to get a square product. 4 times 9, 4 times 25. Because anytime you go x squared times y squared, you get the square of xy. So if we just look at choosing 2 squares, we can count a bunch of ways. We can count a bunch of pairs whose product is a perfect square. So let's just look at the squares first. 25, 36. I choose any 2 of these, multiply them together, I'm going to get a square. 4 times 16, that's 64. 9 times 25, 225, it's 15 squared. So now I want to count the number of ways that I can choose a pair of these. Well, I could choose the first one in 6 ways, and then once I've chosen the first one, I've got 5 choices left for the second number. But I have to be careful here, because choosing 36 and then 16, that gives me the same pair of numbers as choosing 16 and then 36. Don't care about the order, so I count everything twice when I do 6 times 5, so I have to divide by 2 to give me a total of 15 pairs of numbers, 15 pairs of squares, and when I multiply these squares, I'll get another perfect square. But maybe there are more pairs. We have to look for some others. Are there others? Now, thinking about constructing others, well, let's try to make just one. Imagine we choose 2 first, and I want to multiply 2 times something and get a perfect square. Well, now I'm going to need a factor of 2 to go with that first 2 in order to get a perfect square. 2 times 2 gives me the 2 squared. And, well, I need this number to be different from that number, so I can't just stop at the 2. But, if I throw in a square here, when I multiply these two, I'm going to get 2 squared times 3 squared, and that's a perfect square. And same thing if I did 2 times 4 squared. I get 2 squared times 4 squared. So, well, we see that there are more right away. I mean, this is 2 times 18. That gives me 36. So this isn't the end of the story here. We're going to be able to construct some more pairs whose products are a perfect square. And we've got some clue here how to do that. But, oh, now wait a second. You can kind of mix and match these things. 2 times 3 squared times 2 times 4 squared. If I multiply those two together, I'm going to get 2 squared times 3 squared times 4 squared. And yikes. This is basically just like what we were doing here. We multiply 2 squares, we get a perfect square. We have 2 times some square times 2 times another square. We're going to get 2 squared times each of those other squares. We're going to get another perfect square. Check this out. Let's look at exactly what we're doing here. We're starting off with 2 times y squared, and we're multiplying that by 2 times z squared, and we're getting 2 squared times y squared times z squared. So anytime I multiply 2 times some square times 2 times another square, I'm going to get a perfect square. So now I just need to look at the numbers that are twice a perfect square. That's 2 times 1 squared, 2 times 2 squared, 2 times 3 squared, 2 times 4 squared. And then I count the number of ways I can take 2 of these. Anytime I take 2 of these, multiply them together, perfect square. Of course, there's nothing special about the 2 that's sitting right there. Could replace that with 3, replace that with 4, replace it with anything. Let's go ahead and try that, replace it with anything. Of course, we call anything a variable. If instead I started with x, and I'm going to multiply it by something else, and I want to get a perfect square, I'll put an x over there, and then I can stick any old perfect square in here, any old perfect square in here, and when I multiply these two together, I'm going to get x squared times y squared times z squared. That's just what happened up here where we were using x as 2. And at the very beginning, when we were looking at just all the perfect squares, x was 1. We're just multiplying 2 perfect squares. And now we have a way to organize everything we want to count. Very important when you're going to start breaking down into cases. You need a good way to organize it so that you count everything once and only once. And now we're ready to count. And this is how we're going to count. We know that we're trying to count the pairs that look like this. X times y squared, x times z squared. Because that'll come out to be x squared times y squared times z squared. Now, for x equals 1, we already did that. These are the perfect squares. And we found 15 total. We already did that one. Now, when x was 2, well, then we're looking at 2, 8, 18, and 32. These are all the numbers that are twice a perfect square. And we know how to count pairs of this. There are 4 ways to choose the first number, 3 ways to choose the second. Then we have to divide by 2 because we don't care about the order. 32 and then 18, that's the same thing as choosing 18 and then 32. And that gives us 6 total. In this case, then we have x equals 3. So now we're looking at 3 times a perfect square. That's 3. 3 times 2 squared. 3 times 3 squared is 27. 3 times 4 squared is too high. So I only have to choose two out of these three numbers, multiply them together, get a perfect square. 3 times 12 is 36. Well, there are only three ways to choose a pair of these, 3 and 12, 3 and 27, 12 and 27. So that gives me 3 total. Now x equals 4. Well, now I have 4. 4 times 2 squared is 16. 4 times 3 squared is 30. Wait a second. I recognize these numbers. These numbers are perfect squares. Because x is a perfect square. We've already counted all these. No overcounting. We're not allowed to count these again. So you always have to be very careful. You don't want to overcount. So we're going to forget the x equals 4 case and move on to x equals 5. We have 5. 5 times 2 squared. 5 times 3 squared is too high, so there's just one pair. And we have x equals 6. We have 6 and 24. That's one pair. X equals 7. We have 7, and 7 times 2 squared is 28. That's one more pair. Now then you get up to x equals 8, and that's 8 and 32, but we've already got that. 8 and 32, we've already taken care of x equals 8. X equals 9, well, that's a perfect square. You're going to have 9 and 36. We've already found 9 and 36. Already dealt with that. Then you get up to x equals 10. You have 10 and 40, and 40 is too high, so we aren't going to find any more. And now we just finally add them all up. 15 plus 6 is 21. 21 plus 3 is 24, 25, 26, 27 total. And our constructive counting has tackled a really hard problem. And if you think making this video was easy, you know what to do. realmath.org.